Well, good afternoon, everyone. Welcome to another colloquium talk for this year. And it's another example of where we're looking to hear from an LPL faculty member to give us everybody an idea of the range and diversity of all the science that we're doing here. I first met Ilaria when we were both on the science and technology definition team for the LUVOIR mission concept, which is now morphed into HAB Worlds. And I was remembering it was a long time, it was a long committee, and I looked at your CV, it was 4 years. So it was a good chance to work together on a vision for to directly detecting Earth-like planets. So Ilaria joined LPL in 2011, and she became a full professor in 2022. She has her PhD in astrophysics from the University of Heidelberg and a master's in astronomy from the University of Bologna in Italy. She has been recognized by a host of awards, including the Blitzer Award for Excellence in Teaching in Physics and Related Sciences. And she's a fellow of the American Astronomical Society and has served on the NASA Astrophysics Advisory Committee and is chair of NASA's ExoPag Executive Committee. And ExoPag is one of the AGs that is currently on a strategic pause and hopefully will be coming back soon. She also has a host of successful proposals in science with JWST and HST. She's published 170 papers with and has mentored 9 LPL graduate students. And her hometown, Pesaro, Italy, or where she was born, recognized her this past summer as being a outstanding member of the city. Which is very fun recognition I wanted to mention. So with that, I'll turn it over to Ilaria, who's going to tell us about disk evolution and volatile transport in the era of ALMA and JWST.
Yeah, thank you very much, Mark. Can you all hear me well? Okay, that's great. Okay, so I want to start by saying that it's really an exciting time to be able to use these amazing facilities, the Atacama Large Millimeter Array located in Chile, and the James Webb Space Telescope to really learn about the environment where planets are forming. I decided to split the talk in 2 parts. So first I will be talking about what we are learning on disk evolution and dispersal. Then I will pause, take some questions from you, and then I will move into the second aspect, which is about volatile transport. Okay, so let's move into part 1, disk evolution and dispersal. So I want to start with this beautiful picture taken with the Hubble Space Telescope of the Chameleon-1 star-forming region. This is a region that we have studied extensively in my group, both using the Atacama Large Millimeter Array, then Spitzer, and now James Webb. It is about 2 to 3 million years old, and at this age, about 50% of the stars still retain a protoplanetary disk, and they are actively accreting disk gas. If you would look at the younger region, the fraction of stars accreting this gas would be even higher. But this is to say that accretion of disk gas is a common phenomenon, and yet we don't quite understand how this is happening. We know that for gas to flow inward and be accreted onto the star, it has to shed angular momentum. But the question has remained for a very long time, which mechanisms lead to angular momentum loss? So 2 main solutions have been proposed. First of all, all of you will be aware of this classic paradigm of disk evolution. The idea is that disks are turbulent and most of the angular momentum is redistributed outward through the disk, and that enables disk matter closer in to accrete onto the star. In this classic paradigm, you need another mechanism to finally disperse the disk, and this is called photoevaporative winds. Essentially, high energy photons from the central star. They can drive flows of gas from the surface of the disk, but only beyond a certain radial distance, beyond several astronomical units, which is where the hot gas becomes gravitationally unbound from the star. So again, here you need two mechanisms. More recently, theorists have done more detailed calculations of these disks, including microphysics and including also an external magnetic field permeating the disk. And they have found that disks are actually not turbulent in most of the planet-forming regions, so say between 1 and 20 astronomical units. And instead, they have found in their simulations that winds now from all radial distances from the star driven by magnetic field, so these are MHD driven winds, they can essentially remove angular momentum from the disk, and the removal of angular momentums from the surface of this gas disk enables accretion onto the star. So we have done, I led essentially a review chapter on this topic for the Protostars and Planets 7 book, where we highlighted that through this mechanism, you don't need actually photoevaporative winds. You just need MHD-driven winds to drive evolution and also dispersal. And the other thing that we pointed out is that if accretion really happens through this radial extended MHD wind, then we really need to reconsider all of the planet formation models that we have so far. So I'll go back to this point at the end by showing some important aspects. So now the question is, what is the dominant mechanism driving disk evolution? So you can answer this question by approaching it in two different ways. So you can use population level surveys to trace key star disk properties like the accretion rate and the disk mass as a function of time, and then test those against theoretical models. Or you can try to identify these disk winds and characterize them. And there is a kind of a basic prediction here from wind-driven accretion models. Essentially, every accreting star should also drive an MHD wind. And the other major prediction is that the outflow rate in this wind should be comparable with the mass accretion rate onto the star. So we'll see what we are learning by using these two complementary approaches. Okay, so approach one. What you see here are essentially simulations of the classic disk evolution model, the turbulence-driven viscous disk model. So on the top is an initial distribution of disk masses as a function of stellar mass and mass accretion rate as a function of stellar mass. So this is your original population. And we started this way with a large spread at any stellar mass. And then what we do is that we evolve each disk through this classic paradigm. And then after this viscously evolved, we plot the mass accretion rate as a function of the disk mass. And what you notice is that even if you start with a large spread in initial properties, you reach a relatively tight correlation between these two quantities, the rate at which disk mass is accreted and the disk mass itself. And this is really a basic properties of viscous disk model, which many people have pointed out, even starting from early work of Hartmann, 1998. But this is from a more recent simulation that we did. So one thing you might realize here is that when speaking, I said disk masses, but what is plotted is the M dust, which is the dust disk mass. And we did that because at that time, in 2016, this is what we had available through surveys of star-forming regions that we did with ALMA. So now we can compare the expected population with the observed one. And you can see immediately that the observed population of disks, including those in the chameleon star-forming region that we surveyed, has a much larger spread in these two quantities than what the model of viscous discs predict. Now, we were quite careful in the paper to say that we cannot completely exclude these models because there are two things to consider. First of all, it could be that these discs have not significantly viscously evolved. In other words, they still keep track of their initial spread. But we found this possibility quite unlikely because, as I said at the beginning of my presentation, a region like the chameleon star-forming region has essentially lost about 50% of its disk population, which means that at least 50% of the disks have significantly evolved. The second possibility, which we consider to be more likely, is that, well, we observe the dust, but the dust is not a good tracer of the total disk mass, which instead is dominated by the gaseous component. So these results actually motivated a large ALMA program, about 100 hours with ALMA, to study 3 different star-forming regions, a young one, Ophiuchus, intermediate age lupus, and upper SCO, which is an older region. We did 10 disks per region at a sensitivity and resolution to now measure sizes of disks and, more importantly, the gas disk mass. So we have a first round of 12 papers that will appear in March, so stay tuned about that. But for today's presentation, I want to highlight really the very important work that Dinshan Deng, a graduate student in my group, has done for this survey. So thank you, Dinshan. He essentially reduced and analyzed all the data in the lupus star-forming region. And this is a gallery of sources that you will find soon in its paper. But this is to highlight the type of data set that we have. So we have here continuum emission for all these 10 sources in lupus, and we have 3 different CO isotopologues. The more important one for this presentation is the C18O here, which is the rarer isotopologue, and therefore its emission is most likely optically thin. So it's a good tracer of the gas disk mass. So by using this data set, so we calculated the gas disk masses, we had mass accretion rate from previous data, and so we can remake the plot that I've shown you before. Now, mass accretion rate as a function really of the disk mass, so the gas disk mass. So what you see here in red are the data, and the 2 panels show the case of MHD wind-driven disk model versus a turbulent classic disk model. As I've said in the previous slide, here are the simulated data points in black, and so you see that there is this tight correlation as you go to older disks. But the most important thing to point out here is that, again, the turbulent disk model doesn't seem to reproduce the large spread that we see in the data, which are in red. So this is these are some of the main conclusions in the paper led by our collaborator Tabon, that the turbulence-driven models cannot reproduce simultaneously accretion rate and gas disk masses, while the MHD wind-driven model appear to reproduce this observation. Now, these models, they also make some prediction, which of course we should test, but there is also a caveat here written down, is that these models are quite dependent on the evolution of the magnetic field strength, which is essentially unknown. So that is why I think it's also very important to approach this question of which drives, what is driving the disk accretion, the disk evolution, through a completely different approach. And this is through identifying the winds and characterize them. So this is a work that I've done in my group for quite a long time before JWST, using mostly high-resolution ground-based spectroscopy. So we have used IRES on Keck, Magellan Mike, since the facility that we have at the University of Arizona. And what I'm showing here is just a small sample of disks that we have observed at high resolution spectroscopy in this particular tracer, the oxygen 1 6300 angstrom. And with high resolution spectroscopy, we can essentially distinguish different kinematic components. 0 here is the velocity of the star. And as you see, this gas is tracing emission that is blue shifted at different velocity. We have very high velocity, which we can attribute to jets, very fast outflows. And then we have intermediate velocity, which here are color-coded in blue and red, which are compatible with disk swings, and we find them to be ubiquitous. So the set of papers that you see here from my group, they span really a large range in stellar properties and also large range of ages. But because what we have is high resolution spectroscopy, we cannot really pin down the origin of the wind. We see that it's flowing material and is compatible with the disk wind. Then we also did a very large survey with the VLT this year telescope to do the infrared counterpart of these sources. So follow up the neon-2 emission that we had detected in the past with Spitzer. And what we found by combining the optical high resolution spectroscopy and the infrared spectroscopy is that there appears to be an evolution. As the mass accretion rate onto the star declines and disks inside starts to clear out, we find that this oxygen 1 line weakens while the neon-2 emission essentially becomes stronger. So based on this data set, we put together this evolutionary picture that you see here. So on the top, we have a more classic, highly accreting star with large full disks. What is happening at this stage? Again, we have significant outflows at very high velocity from close to the star. And also we see these inner, most likely MHD winds. But because we don't see the ionized neon, strong ionized neon that is flowing from the outer part, we argued that this MHD inner winds needs to be very molecular and massive. But then when the mass accretion rate drops and the inner disk clears out, we see instead the indication of flowing emission from the neon-2, and we find that the oxygen 1 that traces the inner part weakens. So there is essentially a main implication here that there is an evolution also in these MHD winds, and that these inner MHD winds, they are initially massive, molecular, and then they become more tenuous. So if you see here, the reference was 2020, so it was also the time when it was possible to apply for JWST time, cycle 1 time. And so I put in, I led 2 successful James Webb proposals to essentially probe some of these more tenuous wind and some of these more massive winds, and really test this idea that is merely based on high resolution spectroscopy. So let's first look at the more evolved disks. So here we picked 2 disks with large cavities that we knew were present through ALMA observations. And we also knew from ground-based observations that we did that they had this slow flow detected through the neon-2. And so we used MIRI in the IFU mode, and a student, Naman Bajaj, did an excellent work really to find out what is the extension of this emission. So here what you see is neon-2, and he also found that argon-2, which we cannot do from the ground, is extended in one of the sources. So this is the first evidence essentially for what could be a photoevaporative wind spatially resolved from the outer part of the disk. Then with another proposal, we decided to use near-spec in the IFU mode because near-spec has even higher spatial resolution than MIRI. And we picked 4 edge-on system in torus because we really wanted to try to map these possibly extended and massive molecular winds. And so what we found was something quite amazing. So these are the images that we produced using these near-spec IFU data. So the star is here, the disk is edge-on, so you don't see the disk, that's where it's black. But what you see is emission here, it's cut out, but it's iron 2 emission that is collimated in what is a jet. And then we have also H2 emission, so molecular hydrogen in this conical form, which is what is expected from, exactly expected from a disk wind. For the first time, we can see that there is a cavity in these cones. And also for the first time, we detect the wind also in the CO infrared. So it's the fundamental transition. One thing to notice, this is the surface of the disk in the continuum emission, so scattered light from the dust. And you can see that these winds are hundreds of astronomical units above the disk surface. The other important thing to say, this is the composite image, so it's putting them together to really illustrate this nested structure that is also expected from MHD winds. The other thing I want to mention is that here I'm showing just one transition, but we have more than 20 lines that are tracing jets. We have about 20 H2 lines that are tracing winds. So there is a lot of science that can be done with this data. This is one example, is the famous HH30 star, but we have 3 other disks and they all show the same morphology. Another thing we can do is to measure the widths of these jets and also the winds. And importantly, for the first time, we can really trace the emission of these winds down to the disk midplane inside 7 astronomical units, so inside the planet-forming region. So these are that type of winds that appear to drive accretion. For one object, HH30, we can then compare our near-spec data with ALMA. So this in red is now emission in CO, but at cooler temperature. This is the 2-to-1 transition from ALMA. And what we notice here is that this nested morphology of different components of the wind extends even further out at the cooler temperature with ALMA. So essentially in the paper, we go through the detailed discussion, pointing out that the properties that we see for the first time with James Webb, these nested morphologies, these mid-plane intersections, this vertical and radial extent, are not consistent with the X-wind that some of the communities, especially the planetary science community, are used to. They are not consistent with photoevaporative wind, but these are really the radially extended MHD winds that can drive accretion. Obviously, we have only 4 sources, so we would want to see if this phenomena is ubiquitous as it is expected in the wind-driven accretion scenario. These are the spectra, so integrated spectra in the IFU. And I want to show them to you because you can see that there are many emission lines. So it's a very rich data set. And there are also ice absorption features. So there is also interesting things to do in relation to the ice composition in the midplane of these disks and comparing it, for instance, to the composition of comets in our solar system. So this is where I want to stop. These are the 2 main take-home messages from this part of the talk. And again, I want to point out that if accretion is driven really by these MHD winds, then all the planet formation model really needs to be revised. And here are some things to consider, including the redistribution of high temperature material from the inner disk of the solar system to the outer part of the disk. So I will stop here and happy to take some questions that you have on this first part of the talk. And then I'll move to the second one. Yes?
Ilaria, as a theorist, I'm trying to understand the scales. So you're pointing out the turbulence versus the wind model at the beginning. I think of turbulence also as motions too, so gas motions and so on and so forth, but the wind is a directed gas motion. Is one way to think about it, perhaps, or maybe I'm just off base, is that what you're talking about is really sort of supersonic winds or super alphanic if you're talking about magnetic fields, or because turbulence, there's turbulent motions as well. So there's motions and there's wind motions, and I'm just trying to get my head around those two.
No, so the main difference is that in the viscous disk model, the classic scenario, right? This turbulence, I mean, first of all, we don't know what is generating this turbulence, but many theories are telling us that it's related to an instability, the magnetorotational instability, that is also linked to the ionization of the disk. But that turbulence remains essentially in the disk. And here instead, what the theorists are finding is that the gas is not remaining in the disk, but it's flowing outward, and that removal of the gas from the surface of the disk is what enables the removal of angular momentum and therefore the accretion. So they are quite different.
From the disk itself.
Yes, it's a quite different picture.
From the star, right?
Yeah, not from the star. Yeah. Yeah, Mark.
What's responsible for the continuum in the spectrum?
So here we have, I mean, there is, in part, there is the star emission, but these objects are also accreting. And so on top of it, there is also continuum emission from the accretion and from the disk. They also have disk, so dust emission, yeah. Yes, Ty, yeah.
So maybe going back to the image of HH30, I had a question about asymmetries in the jets, which seem to be pretty common. Is that just a projection effect, or is there more wood?
Okay, so we have gone. So this is a very important point. So we actually, in the Nature Astronomy paper here that we published, we pointed out that the asymmetry, sorry, let me go back here. The asymmetry is quite prominent in this object as well as in this other object. These ones not, these are more similar. But here, for instance, you can see that the wind is only on one side. So this is actually a prediction of the MHD wind models that because of the Hall effect, which is a non-ideal MHD effect, you wouldn't necessarily have symmetric winds and symmetric jets. So this was one thing that we said further corroborates the MHD wind model. However, at that time, we didn't have extinction maps on both sides, which now we have thanks to the work of Naman. And so we didn't make a strong claim. But if you look at the extinction maps, they are not that different on two sides. So I think this is further evidence. Thank you for the question. Yeah, Tom?
That's so not my field, but you had a caveat at the beginning of your talk about the B field.
Yeah.
So does the model itself have that as a function, and is there any parameterization of that from like what we know?
Yeah, no, so we don't know almost anything. So
we know from samples, for example.
Yeah, so you can take the average field, for instance, from sample, but then we don't know how it has evolved, which is the main point of this type of simulations. So yes, there is an assumption there on the evolution of the magnetic field, and so that is why I think that while those type of tests are important, looking at the evolution of the mass accretion rate and disk mass, this other method is important too, because it's really looking at the main product of wind-driven accretion, which are the winds. Maybe this is the last one. So go ahead, Andrew.
Yeah, sure. Sort of a follow-up on those other questions. So, I mean, you mentioned it right, that the magnetic field is one thing that can vary, but I mean, these turbulence models seem to have this very tight fit. But of course, the turbulence models have hugely uncertain parameters that could vary from system to system as well. And so why couldn't that generate some of the spread, just turbulence being different with time and different disks and over time?
So Okay, so all these models, and also just to clarify, all the models of planet formation, right? They assume that there is a simple power law dependence of viscosity with radial distance from the star. So this is what enters in all these models, as well the models that I've shown you after of Tabon. So if the viscosity is more complicated, then there can be a bit more scatter. But in this assumption, which is the basic assumption that everybody has been using, this is what you would expect, regardless of initial parameters. Yeah. All right, so now let me move to the second part of the presentation, and I want to talk about, volatile transport in protoplanetary disks. And I want to start this part of the presentation motivated using this plot that shows the carbon to oxygen ratio as a function of radial distance in a protoplanetary disk that is a static disk. So here in solid line, you have the C2O ratio in the gas, and in dashed line, you have the C2O ratio in the grains. And these jumps correspond to the location of snow lines in the protoplanetary disk. So this is the water snow line, CO2, and CO. So there is a large body of work in the exoplanet community trying to measure the carbon to oxygen ratio in the atmosphere of the giant planets and connect it to the birthplace of these giant planets in the disk. So this is a recent example, also using JWST data, retrieve the C2O ratio in comparison to the mass of the planet, and then trying to connect to the birthplace of these giant planets. Now, in doing that, there are some caveats that one has to be aware of. First of all, the star and disk evolve, as we have seen before, which also means that the snow lines are not fixed at this location, but they would change with time. But the other important caveat is that dust grains are not fixed at their location, they drift inside, and that is also impacting the C2O ratio. So I want to first highlight what is the physics of this radial drift. So here you have a schematic grain, which is subject to gravity and centrifugal forces, and it moves on a Keplerian orbit. And here you have instead a parcel of gas, which also is supported by pressure, and therefore it moves at sub-Keplerian velocity, which means that when grains move in this disk, they feel a headwind from the gas, and they start to lose angular momentum and they move inside. It turns out that the solids that drift the fastest are those with a stopping time about equal the orbital time, and at tens of astronomical units, the fastest drifting solids are millimeter, centimeter in size, which in our community we call pebbles. I know that this can mean something different for other communities, but for today's talk, just think of millimeter, centimeter grains when I say pebbles. So now this is a schematic picture of a disk. Imagine that you have a pebble beyond the water snow line. So this pebble is coated with ice on top. And imagine that that pebble starts to drift inward, and it passes the water snow line. So when it does that, then water vapor is released in the gas phase. And therefore, the carbon to oxygen ratio inside the snow line is going to change due to these inward drifting pebbles. In addition, when you start to drift these pebbles inward, you start to have also more material to form your planets. And in fact, this idea of using pebbles to form the planet has been pointed out a number of times in the literature to explain the many sub-Neptunes and super-Earths that are detected, for instance, with Kepler inside 1AU. I have this picture here to remind everybody that some people also believe that the rocky planets in our solar system formed through this same mechanism requires significant inward drift of outer pebble towards the inner disk. Obviously, when you have a giant planet or a proto-giant planet there, the drifting of the pebbles will be somehow slowed down, but nevertheless, some groups believe that you can still form rocky planets in our solar system through the pebble accretion. What was very interesting for me when reading these papers on pebble accretion is that pebble accretion is not an efficient process. And in fact, to form objects that have a mass of less than 10 Earth masses, you need 10 times more icy pebbles from the outer disk to move inward. So given that, a few years ago, I thought, well, maybe we can test this pebble accretion scenario by using the complementary information that we have from ALMA and infrared spectroscopy. Because with the Atacama Large Millimeter Array, we can observe pebbles, icy pebbles in the outer part of the disk. And with infrared spectroscopy, we are sensitive to gas at hundreds of Kelvin that probes the surface, the inner surface of protoplanetary disk, and maybe also probes water vapor released by these inward drifting pebbles. So even before JWST, we could start to address this question. And so we asked, is there any evidence that outer icy pebbles are drifting inside the snow line? And so now I want to illustrate what was our thinking. So imagine that you have disks at birth that are born with dust sizes that are relatively similar to each other. After some time of evolution, after a few million years, if there is a significant drift of these pebbles, some of them will look small and have more water vapor inside the snow line. And those that instead did not have enough drift of these icy pebbles, they will look larger and have less water vapor inside the snow line. So this is essentially what we tested using the Spitzer and ALMA data. So we gathered the largest sample of disks around solar-type stars that have infrared spectroscopy and millimeter dust disk sizes to look at the sizes of these disks. And what we found is essentially anti-correlation between the amount of water that is detected at infrared wavelengths inside the snow line and the size of in pebbles of these disks, essentially along the lines of what we were expecting. So in this paper, we said that based on this type of data, we have some hints for large-scale pebble inward drift. Now, that work really motivated many of the JWST proposals. Many of them were accepted to follow up on that idea. This is one of them. And so what I'm showing here on the upper part of this slide is the advantage of using James Webb MIRI in particular over Spitzer. So now what you can see here are many more water lines. You can deblend many water lines that you see blended at the Spitzer resolution. And you can also identify water lines that have different upper energy levels, so probing gas at different temperatures. And so one thing that can be done is now doing this same plot where we used a different molecule to see what was happening to water, now using water at different temperatures. So this is a line ratio of relatively cooler water, so upper energy level of 1500 Kelvin over very hot water. And here we see again a larger spread, but we see an anti-correlation between the presence of cold water that could be delivered by pebble migrating inward and very hot water that is in the inner part of the disk. So we have about now, through a larger collaboration in the US, we have about 100 planet-forming disks with a large range of ages, including the H-Pro disk that I discussed before, that we can now analyze at the resolution and sensitivity of MIRI. So stay tuned because there will be many more results along these lines. So another thing that we can do with MIRI is that we can move beyond doing line ratios, and we can instead retrieve the properties of the gas. So for instance, the emitting temperature, the column density of these molecules, as well as the emitting radii. So this is work that we pointed out before JWST with an undergraduate student at Stewart. And so what we did is simulations of spectra at the resolution of MIRI with different water content in the inner disk, and then we retrieved those properties of the gas and showed that MIRI will be able to discriminate down to a factor of 5 difference in the column densities of these disks. And we used a local thermal equilibrium slab of gas with varying temperature and a column density to do this type of work. The key question that most of the people are trying to address here is how much mass in pebble has drifted inward? Is that really these 100 Earth masses of pebbles that are needed for pebble accretion, or is it much lower? So this is something that many people are working on now. Now, switching a bit, what I told you so far was about sun-like stars, but there are very interesting results coming out on the low mass end of the stellar spectrum. So here on the top is the TRAPPIST-1 system everybody's familiar with. The central star is a 10th of the mass of the sun. But here there are 7 planets, 3 of which are in the habitable zone. And to scale, all this planetary system is inside the orbit of Mercury. A lot of time has been allocated on James Webb to study the atmospheres of these planets. Before JWST, we already knew that the gas inside the snow line of these disks was very different. So this is work showing median normalized spectra at low resolution of Spitzer, and you can see this molecule C2H2 being much stronger than this other one in this around very low mass stars, which are in green with respect to sun-like stars. And this is slightly higher resolution, again with Spitzer. And we noticed that there were no water lines in these very low mass disks, while the sun-like stars have a lot of water vapor in the inner part of the disk. So already at that time, we concluded that the gas inside the snow line of these disks is oxygen poor and carbon rich. Now, I was really delighted to see the follow-up JWST spectra of some of these Spitzer data, because this is how they look like. So this is a science paper that I could contribute to. I was very happy about. Here you see tons of hydrocarbons and no water line whatsoever, much higher resolution, much higher sensitivity than what we have with Spitzer, no water. These bumps that you see here that one would think are due to dust emission are instead optically thick emission from C2H2. So again, tons of hydrocarbons. Here you can see ratio of column density of the C2H2 with respect to water and C2H2 with respect to CO2, orders of magnitude difference with respect to sun-like stars. Now, there are always exceptions in life, and so I was happy that a graduate student, Cheng Yanji, here at the LPL, actually found the water-rich spectrum from a very low mass, this around a very low mass star. So this is the MIRI spectrum. Here is a model, and you can see this water line. This object was not observed before with Spitzer, so it's a new discovery, and it's a strange object because its disk is very massive. So here you can see the object colored in red because it's a very low mass star, but in terms of millimeter flux, so in terms of dust disk mass, is actually comparable to that of sun-like stars. So we'll try to put this in context later, but for now, I wanted to point it out. Then with Sagan fellow Fen Long, who's also working in my group, we had a successful JWST cycle 2 program to target the oldest TRAPPIST-1 disk analogs, these Peter Pan disk. And so one spectrum is already out, and it's a beautiful spectrum. Again, showing a forest of hydrocarbon lines, maybe tiny bit of water there, but it's debatable, and showing also, demonstrating that this old object, 30 million years old, has still a primordial disk, because we detect H2, a molecular hydrogen, and we also detect ionized neon, and neon is very volatile, so there is no way that this is a second generation dust. More similar, all disks are being analyzed, and another thing that is pointed out in the paper is where we put together the data for different disks around very low mass stars. So SE114, the one that is water rich, is here, and essentially is an outlier in this population. And the other disks, instead, they plot here in this plot. So they plot towards a high carbon to oxygen ratio, exactly as you need to create so many carbon-bearing species. So now you might be convinced that these inner disks are very different from those of sun-like stars, but the question is, why would we have such a high carbon to oxygen ratio in these disks around very low mass stars? And so this has been a question for over a decade, and most of the models weren't actually able to explain what was happening. So I'm going to show you instead a disk evolutionary model that can explain the data that we have so far. So this is a classic viscous disk, but the viscosity is very low, it's 10 to the minus 4. And in these disks, dust is not set at their location, but is also migrating itward, depending on its size, and collisions can also fragment. So it's a full gas and dust disk evolution model. And what you see in this panel is on the y-axis, the time evolution. So the time increase is moving up. Here is radial distance. This plot is for a very low mass star disk, TRAPPIST-1 analog, and this is for a sun-like type disk. The color coding is for the C2O ratio. So if you see blue, it means that there is water vapor, and if you see red, it means that there is a very high carbon to oxygen ratio. And so what you can see from this figure is that the region inside the snow line for these two disks remains much bluer, so much more water rich for a long time for the sun-like stars. And this is due to two things. First of all, the icy pebbles from the outer disk migrate faster around very low mass stars. And when they release the water vapor inside the snow line, because the snow line is so close to the star, the water vapor is accreted onto the star and dispersed also faster. So all in all, there is an important implication here that the terrestrial planet-forming region of disks around very low mass stars, the TRAPPIST-1 analog, maintains a high carbon to oxygen ratio throughout most of the planet-forming region, which is not the case for the sun-like stars. So I think we should be really thinking about this question. What are the consequences for planet formation and evolution for this type of planets? So this is where I want to conclude the second part of the talk, and essentially the entire talk, with these two take-home messages, and then stress again that I think there is a lot to do in this direction. This is really an unexplored region, understanding, for instance, what is the core composition in this carbon-rich environment. Would the evaporation of this carbon-rich atmosphere be the same as those of the primordial atmosphere of Earth-like planet? And what about other effects like plate tectonics and second-generation atmospheres? So I leave it there, and I hope that these results will spark some interest in all of you. Thank you.
Thank you for that great survey, Ilaria. Do we have any more questions? Tom?
So again, not my field, but the C2O ratio has implications for the chemistry, right?
Yes.
That of the solids that could form. So could you test that by looking at the dust?
Yes, so that's actually what I was trying to do already from the Spitzer time. So these disks, they don't show, these disks around very low mass stars, they don't show really prominent silicate features. They are more flatter. And for instance, these two that were published, where is it? They have very weak features. In general, for the other few that we studied also with Spitzer, we see a bit of a silicate emission feature, but it's difficult to quantify the amount of carbon because carbon doesn't have any spectral feature, right? So yeah, that's the problem, essentially.
How much do you have to worry about the grain sizes and the size distribution washing out the silicon feature?
Yeah, that's another good point. So in general, I don't have the figure here, but already from the Spitzer time, we found broader feature in the silicate emission, which suggests that grains are also larger on average. So it could be, yeah, that some features are also washed out because grain sizes may be larger in this disc. So to answer your question, yes, the prediction for dust would be different, but it's difficult to test it that way.
Sorry.
For the pebble drift scenario, the models you presented, the data you presented, were looking at water sublimating off of the dust. What about other volatile species? Could you study this also with, say, CO2 coming off of?
Yes. Yeah, no, that's a very good point. So water, we started with water because it was the more prominent, right? But yes, the idea is that this can be extended to other features, including the CO2, because that is the next snow line that you see that is prominent in a protoplanetary disk. So yes, once we manage to get all the column density for all these different species, we can consider that as well. Yeah.
Do you have any questions online? Do you see? Or last one from the audience.
Thank you, Larry, for the great talk. So a small, around M dwarfs, infrared excesses that could be due to, for example, debris from a planetesimal belt after formation has been really low. Something around like 4% of M dwarfs are thought to have a debris disk that we can detect. Can this fast transport of pebbles into the inner disk explain a smaller planetesimal belt that's seen after the protoplanetary disk phase?
So I think that, I mean, the debris that you are seeing, right, would be second generation dust due to the collisions of leftover planetesimals in the disk. So I think it's more likely that the leftover planetesimals is not that prominent in this disk, and so it's producing less second generation dust. In relation to pebble accretion, maybe if pebble accretion would be more efficient in these disks, then you might be left with fewer of these planetesimal. Perhaps that's where the connection comes from.
Okay, great. Well, thank you very much, Ilaria. Let's thank our speaker again.